I've got a dramatic demonstration of this, okay? Yes, and hotter too. Yes. Okay, now I have a dramatic demonstration. Check out this rubber band. Now, pick one of these things as us. Let's pick this one. This is where a very large nose helps. That one? Am I pointing at one? Yeah. There we go. Now, watch, I'm going to expand it. Notice that this is a one-dimensional universe. I think I can wrap my mind around that, yes? Okay, now watch. As I expand it, notice that every other dot is moving away from that dot, isn't it? Yeah. Yeah, now the next time I want you to observe something more subtle. Let's pick this guy again. Notice that the farther away something is, the faster it moves away, yes? Yeah, do you see that? Yeah, there we go. So the farther away, the faster you go. And now let's pick a different dot. Is it true for any dot? Let's try this one. Yeah? Is it true for that one? Yeah, it's equally true for all of them. If you stretch a universe, right? And a one-dimensional universe is the easiest one to picture. Everything moves away from it. The farther you are away from it, the faster it goes. And this is, of course, why Hubble is so famous, right? He actually figured this out, right? Okay? But we're ahead of ourselves. I think we need to do Doppler effect first. Okay? Okay. So this is the Doppler effect. The notion is if we're sitting still, the wavelength is the same in all directions, that being just the length between the crests of a wave. But if we're moving to the right, okay, we actually make the waves in front of us a little bit shorter because we're moving toward them, and the ones behind us actually get a bit longer. So all redshift calculations, we're going to be doing this longer thing. And then this is a very approximate formula. The notion is that if you wanted to find, and I think in your note guide I gave you the real formula. That's a relativistic formula that will give you the new wavelength. But I'll show you how to do these wavelengths. Okay? Okay. So what is the change in wavelength of the 656 nanometer line? That's times 10 to the minus 9th meters. So wavelengths of light are okay. So our formula is change in wavelength is to wavelength, right? Equals whatever that velocity is to the speed of light, right? So I'm going to call c. This guy is always going to be 3.0 times 10 to the 8th meters per second. Okay. These wavelengths are typically in nanometers, and 1 nanometer is 10 to the minus 9th meters. Yeah? Okay, so let's calculate this guy here. The change, we want to find the change in wavelength, right? So the change in wavelength is to 656 nanometers. And I'm not going to go and put it, you don't have to put it into meters. This is just a ratio thing. Our answer will be in nanometers. And that's what we want. Okay? Equals, let's see, it's 20,000 kilometers per second. So that's 20,000 times 10 to the 8th, 10 to the 3rd meters per second, right? Over 3 times 10 to the 8th meters per second. I know that's not proper scientific notation, but that's the safest way to put 20,000 kilometers per second. Whenever you see kilometers, just say times 10 to the 3rd, right? Now, how are we going to solve for this guy? Do we just cross multiply this times this divided by this? Yeah, so take your calculator and calculate what this guy has to be. Go this times this divided by this. Leave that in nanometers, so just type 656. 656 times 20,000 times 10 to the 3rd. Don't forget to say times 10 to the 3rd, right? E3 divided by 3E8. 43.7, yeah. Right? So this in my calculator looked like this. 656 times 20 divided by 3E8. That's what I typed, literally. You could be clever and figure out that this is 2 times 10 to the 4th, so that's really 2 times 10 to the 7th, right? That would also work. But I'm notoriously bad at like counting zeros myself. So, are we good? Do we get 43.7? Yeah, now if it's moving away from us, what's happening to the wavelength? Is it getting shorter or longer? It's getting longer, right? So what we do is and we're sort of stretching the limit of this formula, right? But the new wavelength is going to be 656 plus 43.7, right? Because it's getting longer. Right? What is that? It's close to like 700, isn't it?
699.7.
Yeah. So the new one is 699.7 nanometers. So you'd say it's about 700 nanometers. Now, if you are like talented and gifted, and I know many of you are, okay, you can try that other formula. The way you do that other formula is you do this, okay? You go, and this is the real formula, right? That the new frequency is what we're trying to find, right? Is the 656 times the square root of it. Now this is going to require some doing, right? 1 plus 20,000 E3 over 3E8. It's a little more complicated, but it's more exact, right? And then you go 1 minus 20,000 E3 over 3E8. Right? This requires, by the way, parentheses inside there. So you're going to have to go square root, parenthesis, numerator divided by parenthesis denominator. Like that. In all these calculators, right? If you do that, you get a number that's very close to this. That answer is right. This one's just slightly off. And the reason that it's slightly off is that this is not a lot slower than the speed of light. It's got to be much, much slower than the speed of light. And this is 2 times 10 to the 7th. That's getting up there, right? 3 times 10 to the 8th is the speed of light, so, you know, it's 2/30ths the speed of light. Not small enough. I don't know. Kind of like a mullet. Let's see if it runs, if we can get the Java applet to work. Yeah, you can't open the specified file. Well, did you even try? Did you even try to open it? Here. I think I've got, I don't know where it is. Maybe it's in there. I tried to. Wave demos. Not that one. Doppler. Wave demos. Is it old? Maybe it's in there. You see Doppler? There it is. Doppler, there it is. Oh, try it and run it this time. Okay, start. That's kind of fun. Somebody made this cool thing, right? So there it is moving across, right? What if I make the source speed faster than the wave speed? Oh, reset. Okay, stop. There. Okay. If I make the source speed faster, it's like, let's make the wavelength shorter. It's like, looks like a motorboat on a lake. And that's because, of course, that's what motorboats are doing. They're going faster than the ripples on the lake. That's why the wake comes out behind them. If it's sound, then it does the same thing it's a sonic boom, right? Yeah. Yeah. Okay. And only you can't go faster than the speed of light in a vacuum, so you can't do like a lightic boom, which is sad. You can go faster, though, than the speed of light in water, because light slows down in water. Okay. Expanding space. Put that in your notes. So try that one. What is the recession rate of a galaxy whose 656 nanometer line comes in at 691 nanometers? Try that one. Do you have room to put it in there somewhere? Do you have room? You could put it down here. So see if this question is, see if you can calculate this V. Yeah? And I'm telling you, well, I'm not telling you this, right? This thing here is 691 minus 656, right? This guy here is 656, right? This guy is 3E8. Physics. See if you can figure out what this velocity is. So what is that? 691 minus 656? 35. Okay, so 35 is